Everybody. I'm going to talk about something bizarre that's in Swedish. And Jan gave me this title, and I had no idea what I was supposed to talk about. But I went to AI, so I'm not going to be fired anytime soon yet, because I'm one of the good guys using AI. And I found that nycklen translates to key. So what Jan wanted me to do was to look at FD, FI, FA as keys for giving low flow anesthesia, key to low flow anesthesia. I'm sure that this message came from Jan because it's nycklen, not nycklen. So there is a typical spelling error in there that absolutely proved to me that this was a message from Jan. So I'm going to talk about definitions of FD, FI, and FA. I'm going to present the case report, and then I'm going to finish with my recommendation on how to use low flow. So first, the definitions. And in order to represent the definitions, this is a typical diagram of a circle system, an anesthesia system, where you have the fresh gases coming out of the wall, no nitrous oxide anymore, but oxygen, air, and your vapor. And that results in a delivered concentration, FD. What you have in the inspired limb is the inspired concentration, and what you have in the alveoli is the alveolar fraction. And let's go over the alveolar fraction. What is FA of a gas? We cannot measure it directly because we don't have access to the alveoli. It can only be approximated by determining end-tidal fraction of the gas or arterial. But since arterial measurement of the partial pressure of an agent is not that simple to do, we can almost exclude that completely. This is a diagram that was used by Philip Payton in one of his studies published in 2020, and that shows the gas exchange process in the lung. To make it a little bit easier to comprehend, I introduced three color-coded segments of this cartoon. In the upper segment, we have the alveolar dead space compartment, where we have a bypass of gas going directly from inspired concentration to expired concentration. So that is dead space, and that is basically wasted ventilation. In the bottom part, we have the shunt compartment, where we similarly have blood shunting from pulmonary artery to pulmonary vein, not contributing to gas exchange. And then we finally, in the middle, have the ideal compartment, where we have an equilibration of partial pressure in the alveoli and capillary pressure in the pulmonary capillaries. This also explains to you why measuring end-tidal concentration will never directly give you a perfect idea of the alveolar partial pressure, because you have dead space, cannot eliminate that. Similar is true with shunt. Measuring arterial partial pressure of a gas, even if you are interested in doing it, doesn't give you an ideal, good number approaching alveolar partial pressure because of a shunt. And dead space and shunt are significantly worse in sicker patients. So there is no good way to determine alveolar partial pressure of a gas. So the ideal compartment in the lung is basically a concept. It does not really exist. And FA of gases are estimated and are calculated based on FE and FT. Okay, I'm getting there. But again, FA is not really very practical to determine alveolar partial pressure of gases, even if it was close to the number. I swear I didn't see Philip Payton's slides. I know I have the same slide here as he had in his presentation. I had no idea. This is the Riley model that you heard about already. This is the normal ideal alveolus. This is the idealus where there is no ventilation. In other words, there is pure shunt. In this alveolus, you have no circulation. There is purely that space ventilation. And you have a VQ ratio that goes from normal to 0 to incredibly high. And all the alveoli are lined up on this graph between the 0 and the very high VQ ratio. And they always represent a different PO2. So even if you were to be able to measure an alveolar fraction of a gas, which you cannot do, all of these alveoli lay on this line, and they all have a different VQ, they all have a different PaO2, all of a different PaCO2. So you cannot come up with anything that's meaningful. Still, there are formulas where we do use alveolar fraction of gases. In the shunt equation, we use alveolar concentration of oxygen. It's impossible to have this in a formula because we cannot measure it. So this is clearly an approximation. So be careful what you're reading because it may not be completely true. So why do I mention this? Because terminology is important. If we want to communicate properly, then we have to use the proper terms. And therefore, I propose that we should stop using FA, alveolar fraction, unless we specifically talk about a method where we are going to calculate FA, an average FA, such as what Philip Payton is doing. Instead, we should use the correct terms, end-tidal fraction or FA, because these are parameters that we can measure. Although again, F arterial is very hard to measure. So Payton is excused for using FA here, and because he really means alveolar partial pressure of CO2. He's serious. He is not just estimating it based on NT. He's really calculating it. So let me present you with a very short case report. This is what I got through the ASA monitor about half a year ago in February. And they give case reports for educational purposes. In this case report, they present, I'm going to go over this quickly, 74-year-old man, 4th hour of radical pancreatectomy, general anesthesia, of course. Anesthesia has been maintained with 2% sevoflurane and air oxygen, 2 liters of crystalloid, 4 units red blood cells, blood loss 1500 ml. He became then progressively hypotensive over the last 30 minutes. Which of the additional monitors would you recommend? Transjugular venous oximetry, PA catheterization, or transesophageal echocardiography? Who would choose one of these 3? Anybody? You would not do that, what they ask you to do. You have to choose one of the 3. 3? Michelle, you're not agreeing? You would what? You would blame the anesthesiologist? Replace. I think that's a very good idea. Because the information that we are getting here is is totally incomplete. Anesthesia is maintained with 2% sevoflurane. What does that mean? I don't know. I have no idea. Do they mean, is this the vaporizer dial setting? If it's the vaporizer dial setting, what is the fresh gas flow? Is it inspired fraction? Is it alveolar fraction, which they cannot measure anyhow? Is it end-tidal fraction? We have to guess. So let's say it's end-tidal fraction, which is what we should report routinely anyhow. So let's say it's end-tidal fraction, 2%. The MAC in a 74-year-old man is 1.45%. So this patient got 1.38 Mac of sevoflurane for a couple hours probably. So Michelle was correct, I would replace the anesthesiologist. This is a massive overdose in my book. So again, proper terminology is important to communicate effectively. Now low flow. What are the advantages of low flow? I'm not going to go over this, we all know this. What are the consequences of low flow anesthesia? The first consequence is that the vaporizer dial setting does not correspond anymore with the inspired partial pressure. And why is that? Because there is rebreathing of gases with a lower concentration of what is dialed in. So you're reducing the delivered concentration by rebreathing gases with a lower sevoflurane concentration. There is also a difference between the dialed concentration, FD, and end-tidal concentration, which we use instead of FA. Why is that the case? Because there is uptake of anesthetic by the patient. So the concentration of sevoflurane decreases over time because of continuous uptake of sevoflurane in the alveoli. If you suddenly, in the middle of a case, reduce fresh gas flow significantly, let's say you go from 3 liters to 1.5 liters, you have a sudden change in FD and, in FI. The difference between these two parameters becomes larger because you have more rebreathing here, so there is more dilution of the delivered gases, and the difference between vaporizer dial setting and tidal concentration becomes larger also because you have inhalation of gases with a lower concentration. And if we assume that the rate of uptake stays relatively constant over that time, there is more sevoflurane removed by the patient than is inspired into the lungs. So these differences become larger. So people don't like to change the fresh gas flow suddenly in the middle of a case because the numbers don't match anymore and they like to use matched concentrations. Question is, what is the minimum fresh gas flow? How low can you go? And Jan has talked about it several times in these meetings. But the minimum fresh gas flow has to at least equal the amount of oxygen that the patient takes up and has to replace the gases that are being sampled by the normal gas analyzer. In most places that I know of where low flow is used, these sampled gases are returned to the circuit. So there is no loss there. In other words, we have enough with about 150 to 200 mL of oxygen per minute, which is the average oxygen consumption of an average adult at rest. And I would say that under anesthesia, they are at rest. Many years ago, Jan determined in 2001, that's 24 years ago, Jan determined the vaporizer dial setting that is required at any fresh gas flow to maintain an end-tidal concentration of 1.3% in oxygen. So he used several different fresh gas flow and then recorded the vaporizer dial setting that was necessary to maintain the end-tidal at 1.3%. And then you have a bunch of lines. In the x-axis you have time. Here you have vaporizer dial setting. And the one that we are somewhat interested in the open circles, where the fresh gas flow is 1 liter per minute. And you see that it's a fairly straight line starting at about 15 minutes. In the beginning, you need a lot more agent to wash in the circuit and to compensate for the high uptake at that point. But pretty soon it stabilizes. After 15 minutes, you can do with 1.9 to 2.1% sevoflurane vaporizer dial setting. This whole combination of graphs, you can now transfer that into a plane. And that plane represents fresh gas flow, time, and vaporizer dial setting in the y-axis. And as long as you have a combination of fresh gas flow, vaporizer setting, and time that allows you to stay on that plane, you will get an end tidal concentration of 1.3% during maintenance. Of course, at the beginning of the case, if you use low fresh gas flow, you have to follow the upper arrow somewhat, and you have to quickly go with high vaporizer dial setting, but then over time you can gradually come down. This is how a lot of people practice the red line. You go up a little bit on your sevoflurane vaporizer dial setting. This is the three-dimensional curve. So this means that this point is at about 2.5%. And you end up with a fairly straight line, so about 1.9 to 2% of vaporizer dial setting will give you 1.3% end tidal, so you stay within this plane. And this is a fresh gas flow that a lot of people use, 1.8 to 1.5 liter per minute, because during maintenance they don't have to change the vaporizer dial setting. This is how I like, or I should say liked, to practice, where from the beginning you use very low fresh gas flow, about 0.3, 0.4 liters per minute. You turn your vaporizer dial setting all the way up, and you, in the beginning, you underdose a little bit. In other words, your end tidal is not at 1.3% because you're not in the yellow plane yet. You're just left of it a little bit. But very quickly, if you keep your vaporizer setting constant, you enter the plane and then you slowly have to decrease your vaporizer dial setting to maintain end tidal at 1.3. This means that you're going to be busy. You're going to be busy changing the vaporizer setting several times. This is one example of what I do at the beginning of the case. 0.42 oxygen, 0.2 air, 8% sevoflurane, and you just wait and let everything go up. Your propofol will make sure that, that your patient remains anesthetized while you're building up the sevoflurane relatively quickly. This is even at 0.25 to 0.5 liters per minute. This is a fairly rapid buildup of sevoflurane. So you're pretty confident that your patient is unconscious, especially after a good bolus of sevoflurane and some opioid, because they work synergistically. So I'm going to skip over the patient, this slide. So when using low fresh gas flow, as I said, you constantly have to change FD, especially with very low fresh gas flow. And also, there is a wider range of D that you have to use from patient to patient, because the vaporizer dial setting depends on the uptake by the patient at that concentration. And that uptake can vary up to 50% from patient to patient. So therefore, FD will vary also. So how can we do that when we are very busy, when we have to do all these things? We don't have time to play with the vaporizer dial setting, but there is a solution for that. And that solution is use automated target controlled low flow anesthesia machine. That takes care of everything and you don't have to worry anymore. And for some people it's interesting because they don't have to think about it anymore. So keep practicing and keep experimenting with low flows. Thank you.